If you follow AI, you know the big goal isn't just AI that sees or AI that creates.
Right.
It's getting one single system that can handle, well, everything. Complex visual stuff, top-notch generation, and even editing itself on the fly.
Mm-hmm.
But can one model really do all that efficiently?
That's the million-dollar question. And
Yeah.
honestly, it bumps right up against some major engineering hurdles.
Okay.
But today, we're diving deep into Lavida-O. It's a new approach, a new model that seems to be tackling those hurdles head on.
Lavida-O.
Yeah, it's built as this single model that unifies understanding, generation, seeing, reasoning, creating, editing, you name it. It's really pushing the boundaries of what one architecture can do.
Okay, so let's unpack this for you. Our mission today is to figure out how Lavida-O actually manages this unification, without getting slow or bloated or forgetting things it learned yesterday.
Exactly.
We're going to look at three key innovations they talk about. This elastic mixture of Elastic-MoT, they call it, for efficiency, something called stratified sampling for quality.
Mm-hmm.
And this really interesting planning and reflection loop where the model basically checks its own work.
It's pretty fascinating. This is basically your shortcut to understanding maybe the next big shift in how multimodal AI is built.
Right. So historically, if you wanted an AI to do a complex task like, I don't know, look at a photo, answer a question about it, then edit the photo based on that.
Yeah, you have to stitch things together.
Exactly. You needed a whole bunch of specialist models, one for object detection, maybe another for image generation, one for understanding the text.
Totally. It's like running an IT department where you need 10 different experts just to fix one problem that crosses hardware and software lines.
Yeah.
And there's just no real synergy. So when you ask for something subtle, like change the lighting on just this object and make sure the reflection looks right on the floor.
Good luck.
Right. The specialist system just falls apart. They don't have that shared, cohesive understanding you need for the really complex stuff.
Okay, so why not just build one giant model then? People tried that, right?
They did. And they ran into, well, a couple of brutal problems. First, training a massive single model, like a big dense transformer. It just eats up data like crazy.
Yeah.
Super inefficient.
Okay.
And second, there's this notorious issue called catastrophic forgetting.
Ah, yes. Catastrophic forgetting. Sounds bad.
It is exactly what it sounds like. Imagine, you learn French fluently.
Okay.
But the second you start practicing Italian, poof,
Yeah.
all the French is gone. Your brain just overwrites it.
Right.
The AI, it means learning a new skill, maybe image generation, could instantly wipe out all the hard work the model did learning to understand images or text.
So those earlier unified models, expensive to train and often pretty slow too.
Absolutely. Many of them are relying on what are called autoregressive models.
Okay.
These generate output step by step, one token, one pixel, one word at a time,
Painfully slow, yeah.
especially for high-resolution images.
Yeah.
If you want a big 4K image, you're literally waiting for thousands and thousands of sequential steps. Not practical.
So this is where Lavida makes a fundamental shift. Right. It's built on something different.
Exactly. It's built on masked diffusion models, or MDMs.
MDMs. Why are they faster? What's the key difference?
Okay, think of the autoregressive model like that single editor, reading a huge document word by word, super slow.
Right.
MDMs work differently. They start with everything masked, hidden, like a blank canvas, sort of. And then, instead of revealing one pixel at a time, they reveal the final image in big chunks, sometimes all at once. They use parallel decoding.
So it's not waiting for piece one before starting piece two. It's tackling the whole thing at the same time.
Precisely. Imagine having hundreds of editors instantly filling in different parts of the same document based on the instructions.
Wow, okay.
This parallel approach makes Lavida-O inherently faster. It means it can handle things like high-res images, manipulating objects, complex edits, much more easily right from the start.
But hang on, parallel speed is great, but does it solve that catastrophic forgetting issue? Or the cost? If you just make one giant MDM brain with, say, 10 billion parameters for both understanding and generation.
You'd hit the same wall.
Yeah.
Exactly. The cost, the inefficiency, it would still be a problem.
Okay.
And that's where the elastic mixture of transformers comes in, the Elastic-MoT.
Elastic-MoT. This sounds like the core architectural trick.
It really is quite clever. They figured out they needed specialized parts, yes, but they didn't need to, double the entire model size for every single task.
Because a standard mixture of transformers, or MoT, would be super expensive.
Hugely expensive, yeah. Lavida-O is much more strategic about it.
So what's the split? How did they divide the labor?
They coupled a really large understanding branch that one's about 8 billion parameters with a much smaller, more focused generation branch, which is only 2.4 billion parameters.
Okay, 8 billion for understanding, 2.4 for generating, total 10.4 billion.
Right. But here's the critical part, the elasticity.
Mm.
They only activate the specific bits needed for the task at hand.
So it's not lugging around the whole 10.4 billion parameter brain if it's doing something simple.
Exactly.
Give us an example. How does that save resources?
Okay, say you just ask for a straightforward text-to-image job. Generate a picture of a blue horse.
Simple enough.
The system only needs that 2.4 billion generation branch, plus maybe the first 16 layers, about 4 billion parameters from the understanding branch, to process the text prompt initially.
So only 6.4 billion active parameters out of the 10.4 total.
Precisely. That's a big saving right there.
That really is a different way of thinking about resource use. And if it's just understanding something, like reading a chart,
Then it only uses the 8 billion parameter understanding branch. That's all it needs.
and the full 10.4 billion.
Only gets used when it's doing something really complex and interwoven, like generating an image and critiquing it at the same time using its understanding skills.
Wow. Okay, the efficiency gain must be significant.
It's staggering, actually. Their numbers show this elastic setup improves training speed by over 3 times 3.17x faster compared to trying to train a standard, non-elastic multi-modal of the same overall size.
Over 3 times faster.
Yeah, and that speed up translates directly into lower costs for training and running the model, plus faster development.
That 3.17x is a huge deal.
Okay.
But okay, I have to ask. You've got these two specialized branches, right? The big 8B understanding one, the smaller 2.4B generation one. How does the system know when to pass the baton? How does it switch between thinking in words and thinking in pixels?
Good question. That handoff is managed by something they call modality-aware masking.
Okay.
Remember, the model starts with everything masked, so it's always predicting what's behind the next mask. By default, it kind of assumes it's text.
Makes sense.
But in the instructions mean it needs to create an image, say, after it reads the text prompt, it outputs a special token, XB. That stands for expansion.
So XP is like a little flag saying, okay, image time.
Exactly like that. And that single token doesn't just turn into one pixel. It triggers a huge expansion. It blows up into a whole grid, maybe hundreds of new mask tokens, all specifically marked as image tokens.
Ah, I see.
And those image tokens, they automatically get routed to that smaller, specialized generation branch to be filled in as pixels.
Cover. So that's how it weaves text and images together without the two branches getting confused.
That's the mechanism, yeah. It keeps things flowing smoothly between modalities.
All right, so we've covered speed and efficiency with Elastic-MoT. That makes sense.
Right.
Now let's talk precision. Lavida-O needs to make sure the images it generates actually look good and follow instructions, sometimes really complex ones.
Absolutely. Quality and control are crucial.
So what did they do to give users or the system itself better control?
Well, the first step is something called universal text conditioning.
Yeah.
This is about making control easier for the user.
Okay.
You know how with some models you have to fiddle with complicated sliders or settings files to adjust things like image style or quality?
Yeah, it can be a pain.
Lavida-O lets you just add those conditions right into your text prompt. Things like desired image quality, aesthetic score, contrast, luminance. You just type it out in plain English.
Oh, that's much more intuitive. So if I want, say, a high contrast film noir look, I just add high contrast film noir style to my prompt. No digging for setting.
Exactly. It puts that fine-grained control right up front in natural language.
Nice.
But controlling it with text is only part of the equation.
Right.
We talked about how MDMs are fast, but how they reveal the image, the unmasking strategy, also matters a lot for quality.
Right. You mentioned a potential clumping problem earlier.
I did. With standard MDM unmasking, the model might sometimes get too focused on one area it's confident about, like a face. It unmasks all the pixels there first.
And the rest of the image.
Can end up looking underdeveloped, maybe blotchy or incoherent because the model didn't spread its attention early on. You get good local detail, but poor overall composition.
So how does Lavida-O fix that? You mentioned stratified sampling.
Yes, stratified sampling. Think about coloring a picture by just putting dots down. Standard sampling might put all your first dots in one corner.
Okay.
Stratified sampling forces the model to spread out. It divides the image into a grid, let's say 4 quadrants, and it forces the model to unmask exactly one token in each quadrant before it can move on.
Ah, so it guarantees broad coverage right away, across the whole canvas.
Exactly. And it does this recursively in finer and finer grids. This stops the model from getting stuck on just one detail early on. It promotes a much more balanced unmasking process.
And the result is better images.
Significantly better, yes.
Yeah.
They mentioned it achieves the best FID score. That's a common image quality metric on benchmarks, validating this approach.
Okay, quality addressed. What about speed on the understanding side? Let's talk object grounding, finding objects and drawing those bounding boxes around them. Why was that slow traditionally?
It was slow for the same reason autoregressive generation was slow. The models would output the coordinates for the bounding box one number at a time.
Like X start, Y start, X end, Y end.
Exactly. 4 sequential steps for every single box. If you have multiple objects, it adds up fast.
So what's Lavida-O's trick here? How did they get it reportedly 6.8 times faster?
The key is coordinate quantization.
Quantization, making continuous numbers into discrete steps.
Precisely. They take the coordinates, normalize them so they fit in a standard range, and then quantize them into just 4 discrete tokens for each box.
Ah, so the coordinates become tokens, just like words or the special X token.
You got it. And once they're discrete tokens,
The parallel decoding of the MDM can kick in again.
exactly, the MDM architecture can now spit out all the coordinate tokens for all the objects in the image, whether it's one object or 10, in a single parallel step.
Okay, that's smart. Aligning the data format with the model's core speed advantage, 6.8x faster, makes sense now.
That's a really neat alignment, yeah.
Now let's get to what sounds like maybe the most intriguing part, this self-improvement loop. Using understanding to boost generation via planning and reflection.
This is where the unified nature really shines, I think.
Tell us about planning first.
Okay, planning is proactive. Imagine you give it a tricky spatial instruction like draw a horse standing above an astronaut on Mars.
That sounds difficult compositionally.
It is. So before Lavida-O even starts generating pixels, it realizes this is complex. It first generates a sort of hidden internal plan. It might be text-based, like a basic wireframe or bounding boxes describing where the horse and astronaut should be relative to each other.
So it figures out the layout, the structure conceptually before it commits to actually drawing it.
Exactly. It solves the structural puzzle first, which is much cheaper than generating pixels and then realizing it's wrong.
Okay, that's planning. What about reflection?
Reflection is the quality check after generation. Once it's generated an image, it immediately uses its big 8 billion parameter understanding branch to look at its own work.
Critiquing itself.
Yes, it compares the generated image against the original prompt. Let's say the prompt asked for 3 red apples on a table, but the model only generated 2. The reflection mechanism, using the understanding branch, spots that mistake. It recognizes, I had generated 2, the prompt asked for 3.
And then?
It triggers a regeneration step,
Yes.
specifically aiming to fix that identified error. It creates a new, improved image with the correct number of apples.
Wow. So it finds and fixes its own mistakes before I even see the first version.
Potentially, yes.
Yeah.
It's an internal loop of critique, improve. That's a fundamentally different level of autonomy and quality control.
Okay, this all sounds very impressive architecturally. Let's quickly touch on the results. Do the benchmarks actually back up this design? How does it stack up?
The results look pretty compelling, yeah. Lavida-O shows really strong, often state-of-the-art, scores across important benchmarks.
Like what?
Well, on understanding tasks, things like the MMB benchmark, chart QA for reading charts, it performs exceptionally well. That validates the power of that big 8 billion parameter understanding branch.
Band generation.
On generation benchmarks like Genevol and DPG Bench, it also holds top scores. This supports the quality coming from the 2.4 billion generation branch and that stratified sampling technique we talked about.
What about comparing it to models people might know, like GPT-4o?
That's probably the most telling comparison. The paper highlights that Lavida-O actually outperforms GPT-4o on specific practical image editing tasks, like accurately replacing an object or removing one from an image.
Outperforms GPT-4o on editing.
Okay, that's significant. It really suggests that this kind of vision-focused, unified, elastic architecture has immediate practical advantages for these multimodal tasks. And it's fast, showing lower latency compared to models like Bagel and GPT-4o in their tests.
And you mentioned this wasn't trained on some secret proprietary data set.
No, which is great for transparency and future research. They used publicly available data, like the big LION-to-B dataset.
Good to know.
And the training itself was structured logically. First focusing on region understanding, then pre-training text-to-image generation, and finally a joint fine-tuning stage to get those two branches working together seamlessly.
Okay, so let's try and synthesize this for everyone listening. We've got the Elastic-MoT saving resources, MDMs providing parallel speed, smarter sampling for quality, and this self-correction loop. What's the big takeaway here?
I think Lavida-O really lays out a blueprint for how you build truly scalable and capable unified AI. It shows that excellence isn't necessarily about one giant slow brain.
Right.
It's about strategically combining specialized, efficient parts, that Elastic-MoT idea, and crucially, baking in sophisticated ways for the model to plan its actions and improve its own outputs, like planning and reflection.
That strategic combination seems key. And the final thought I want to leave you, the listener, with really centers on that reflection capability. Think about it. If a system can genuinely self-critique its own creative work, if it can look at an image it made, identify a flaw in composition or counting or spatial logic, and then fix it itself.
Yeah.
What does that imply? That level of self-contained quality control, that internal coherence? It feels like a step change. We're moving beyond AI that just understands its input. This is AI starting to understand and critique its output.
That's a powerful idea.
It really changes how we might think about the trustworthiness, the reliability, maybe even the autonomy of these systems moving forward, something to definitely keep an eye on.